Hello everyone, I'm Thanatkorn and I'm here with Natthawut and Sunyapat. Today, we are going to explore one of the most important experiments in the history of physics, the photoelectric effect. This experiment completely changed how we understand light, energy, and even the behavior of electrons. And by the end of this video, using this simulation, you will understand why classical physics failed, how Einstein saved the day, and how the photoelectric effect gave strong evidence that light behaves as packets of energy, called photons.
Section 1. The experiment. Let's begin with the experiment itself. Imagine a simple apparatus. Firstly, a metal surface, usually a clean metal plate. Second, a sort of light shining onto that metal. Third, a circuit connected to measure current which tells us if electrons are escaping from the metal. Fourth, a variable stopping potential allowing us to measure the maximum kinetic energy of the emitted electrons. Here's what happened. Light shine on the metal. If electrons are ejected, we detect a photoelectric current by applying a negative voltage. It's called the stopping potential. We can slow down the electrons until the current drops to zeros. The stopping potential gives us the maximum kinetic energy of the ejected electrons. This setup allows us to test how light interacts with electrons in the metal.
Before the experiment, classical wave theory made very clear predictions about what should happen. According to classical physics, light is a wave. The energy of a wave depends on its amplitude, which corresponds to intensity. So, classical physics predicted that, first, increasing intensity should increase electrons' energy. If you shine brighter light, the electrons should gain more energy because more energy is delivered to the surface. Next, any frequency of light should eventually eject electrons. Even low-frequency light, if intense enough, should provide enough energy over time to knock out electrons. Next, no threshold frequency, because there should be no minimum frequency required. And finally, time delay should exist. If the energy arrives gradually, electrons should need time to absorb enough energy before ejecting, especially at low intensities. These predictions are reasonable if light wave is a classical wave, but the real world completely disagrees.
Now, what can we observe from this experiment, this simulation that I'm doing right here? And how does this contradict classical physics? Well, the first observation that I can make, obviously, is that no electrons are ejected below a certain frequency. That is very interesting because no matter how intense the light is, if its frequency is below a certain value, nothing is about to happen. Because this minimum frequency is called the threshold frequency, which is commonly written in equations as F0. And the second observation that I could make from this is that the electron kinetic energy depends only on frequency and not on intensity, because higher frequency lights ejects electrons with higher energy, as you can see, and increasing intensity does not increase electron energy, because it only increases the number of electrons that are emitted. And the electrons, as you can see, are ejected instantly. There's no time delay. As hypothesized before, even at extremely low intensities, as long as the frequency is above the threshold, F0, electrons will be emitted immediately. The fourth observation is that the photoelectric current will increase with intensity, because if intensity increases and the frequency is fixed, more photons can hit the surface, and then more electrons can be ejected, thus causing higher photoelectric current. And the fifth observation, which is very interesting, is that different metals have different threshold frequencies. This is because metals with more tightly bound electrons will require higher frequency to eject electrons. So these are the 5 observations that directly contradict classical physics.
Einstein solved the contradiction by proposing that light is made of particles called photons, each carrying a discrete amount of energy. So the energy of a photon is calculated by multiplying Planck's constant with the frequency of the light. This means that the higher the frequency, the higher the proton's energy. So intensity equals the number of photons per second. Each metal required a minimum energy to eject an electron, called the work function. Since the energy of a photon equals the Planck's constant multiplied by the frequency of the light, then the minimum frequency also equals the work function divided by the Planck's constant. If the photon's energy is lower than the work function, then the electrons cannot be ejected, no matter how many photons there are. After the electron absorbs a proton, the kinetic energy equals the Planck's constant multiplied by the frequency of light, subtracted by the work function. This matches the observations perfectly, since we found that the frequency controls energy, intensity controls the number of electrons, and instantaneous emission occurs because one photon ejects one electron immediately. The photoelectric effect becomes one of the strongest pieces of evidence that energy is quantized.
Section 5. Classical intensity versus photon intensity. Classical model. First, intensity equal wave amplitude. Second, higher intensity equal more energy derived continuously. Prediction: higher intensity equal higher electron energy. And photon model. First, intensity equal number of photon, and each photon has energy independent of intensity. Third, prediction: higher intensity equal more electrons but same energy per electrons. This exactly matches what experiments showed.
Every metal also has a different work function. For sodium, it has low work function, so it has low threshold frequency. Zinc has a higher work function, so it needs UV light. But platinum has very high work function, so it needs deep UV light. If you plot the electron's kinetic energy versus the frequency, you'll get a straight line, where the slope equals the Planck's constant, the x-intercept equals the threshold frequency, and different metals shift the line left or right depending on the work function. Next, if you graph the current versus the intensity, at fixed frequency, current increases linearly with intensity, and a maximum kinetic energy does not change. So these graphs provide strong evidence that the photon model is correct.
All that we have learned today, I am going to summarize it for all of you. Firstly, classical physics has said and has predicted that electron energy should depend on intensity, but we have proven today that it doesn't. And our experiments that we have observed show that frequency determines electron energy, and that there is a threshold frequency, F0, unique to each metal. And the electrons were ejected instantly, even at low intensities. But if you increase the intensity, that increases the current, not electron energy. And we have also explained about the photon model today, which explains all the observations, which are: light energy is quantized, energy of each photon is hf, and the intensity is the number of photons, not their individual energy. Overall, the photoelectric effect marks a turning point. It shows that light behaves not just as a wave, but it is also a particle called photons. Thank you so much for listening today.